It is Thursday, October 22nd, 2020, and there we go. We're going to be looking at the introduction of section 2.2. If you're following along in your textbook, this is about density curves and normal distributions. Okay. So, what is a density curve? That's the first thing. What is a density curve? So here's our definition straight out of the textbook. A density curve is a curve that is always on or above the horizontal axis and has area exactly 1 underneath it. Essentially, if you add up the area underneath a density curve, it will be 100%. It will add up to 100% of the distribution that it's representing. And so in statistics, we call that 1. Because we recall percentages are just a decimal converted to a percent. So all percentages range from 0 to 1. We just take that 0 to 1 and multiply it by 100 to make it that percentage number. So in like statistics and probability, they use those numbers 0 to 1 as like essentially the range of the proportions. It can go from 0 to 1. Right? And so we also have a density curve describes the overall pattern of a distribution. So when we draw the shape over a distribution, that's essentially a density curve. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. We'll look at an example here shortly that will help kind of make more sense of what this actually means. And it all relates back to the stuff that we have been talking about with percentiles and like quartiles and z-scores and things like that. They all kind of help build this idea of a density curve and how to read one. All right. Density curves, like distributions, come in many shapes. A density curve is often a good description of the overall pattern of a distribution. Right, so again, it's very similar to when we draw the shape over a distribution. Gives us an idea of the pattern. Density curves are slightly different because of how they have to be drawn. They must be like kind of right on top of our histogram bars, let's say. Outliers are not described by the curve. That is a key difference between like a shape and a density curve. No set of data is exactly described by a density curve. The curve is an approximation that is easy to use and accurate enough for practical use. Right? And that's kind of a key thing. A density curve is close enough that we can use it. It is not 100% accurate to all the data points, but it's close enough that the amount of error that we have is negligible. All right. And again, in the next slide here, we'll see some examples of a density curve, and kind of how to use it and how to read it. All right. So can you raise your hand if you need time to write some of these notes down from this slide? All right. Shall pause. So now here's our kind of visual representation here for what is a density curve. All right. Over here, all right, we have a histogram representing the ITBS vocabulary score, right? The histogram of the Iowa Test of Basic Skills vocabulary scores of all 7th grade students in Gary, Indiana. Smooth curve shows the overall shape of the distribution, right? So this curve that's going up and over our distribution here is the density curve. Notice that it is not above all of the histogram bars. It's close, it cuts some of them off, it's above some of the other ones. Okay. But this would be our density curve. Okay. We're kind of showing these two graphs of the comparison over here to the right. It's the same graph again, the ITBS vocabulary scores. In graph A, the proportion of scores less than or equal to 6, so this point right here, and the bar is over, in the actual data is 0.303, or about 30.3% if we want to convert that to a percentage. Pretty close to a third. Okay. So if we use the actual proportion from the histogram, right? Take all the numbers, all the amount of values divided by the number of values total, we'll get 0.303. Right? The proportion of scores less than or equal to 6 from the density curve is 0.293. Notice how on the density curve, we're cutting off parts of the boxes here, right, of the rectangles on the histogram, but we're also counting parts that are not counted in the histogram in other places. So it's kind of like we're getting a give and take. And now as far as calculating the actual area under the curve, to do that you need calculus and other math to actually find out the function of the curve, which we're not going to do. You're not going to have to do that for this course. It's not a requirement for this course. Don't get caught up into how to actually calculate that proportion. Super specifically, what we get to do is there's actually tables. We'll get into this probably next week on how to use the tables that tell us the proportion of area under a curve based on the shape. Right. If we wanted to actually calculate it, it takes a lot of work. And that's why there's pre-done tables. They're very long tables. We'll have to learn how to use them, but that is definitely preferred to doing the calculation. Calculation is horrible. Horrible. Yeah, brings back like shivery memories. Ugh. All right. So this is kind of how a density curve is seen and kind of how it's used, right? It kind of goes back to our percentiles and percentages of distributions. If you are writing anything down from this screen and you need more time, please raise your hand. Are there any questions so far? Anything I can clarify? So next we get into describing a density curve. All right. Now, describing a density curve is very similar to just describing a shape or describing a distribution. We use all the same ideas. All right. So measures of center and spread apply to density curves as well as actual sets of observations. All right. So center and spread still get used. Same as in when we just describe a normal distribution, or not a normal, a regular distribution. Don't want to use the word normal. Okay. Areas under a density curve represent proportions of the total number of observations. Okay. So now rather than like kind of counting numbers of observations, we're using area out of 100% to represent the proportion. The median of a density curve is the equal areas point. The point with half the area under the curve to its left and the remaining half of the area to its right. Right? And this makes sense based on how we find the median. Right? A median is that middle point where about half is to the left and half is to the right. Median on a density curve is that point where we have 50% to one side, 50% to the other side of the area. The mean of a density curve is the balance point, as we've kind of alluded to in previous classes. Right? Just like in the distribution, the point at which the curve would balance if made of solid material. Right? So our median is that equal areas point, 50% on each side, 50% of the proportion, 50% of the area, 50% of the observations. And the mean of the density curve is that balance point, just like in a distribution. If it was made of a solid material, where would you have to balance it so that it doesn't topple over? The mean and the median are the same for a symmetric density curve. They both lie at the center of the curve. And again, this is something we've talked about previously, like when we were describing, shape and center. If we have a, roughly symmetric distribution, the mean and median are about in the same place. They're pretty close. If it's skewed, right, the mean is pulled away from the median in the direction of the tail, right, which is the next note. The mean of a skewed curve is pulled away from the median in the direction of the long tail. All right, so all these things that applied to like describing a distribution that we've been using apply to describing a density curve. We use all the same basic principles. And would you raise your hand if you are writing these down and need more time? Excellent. All right, so again, in picture form, if we're looking at these two density curves, right, we have this kind of symmetric one, and the mean and median are in the same place, right there in the middle. And then we have a density curve that is skewed to the right, right? We have the median here that splits the area roughly in half, or basically in half, 50% over here, 50% over here to the right. Then the long right tail pulls the mean to the right of the median. Right? And so that's why we have this little triangle. This represents our balance point to the right of the median. And that's just what this description is giving us. Exactly what I just said in some slightly different wording. Right? So in picture form, this is kind of, again, what we've been talking about. The mean and the median can be estimated or guessed just based on the density curve by finding where we can cut this in half. So 50% is on one side, 50% is on the other side, and where we balance it to the mean. Are there any questions, or is there anything I can clarify so far? And once again, can you raise your hand if you are drawing these pictures or need more time to write anything down? And again, we have this kind of illustration for the balance point here, where we have the mean is the balance point for a density curve. So we can think of this as a solid piece of material. I cannot balance it over here. It's going to tip over. If I go too far to the left, it'll tip over. But this point is just right. And we will balance. So now, we'll get into something slightly different based on the same things we've been talking about. Normal distributions. All right. One particularly important class of density curves are called normal curves. Right? The distributions they describe are called normal distributions. Right? This is why I've told some of you in your individual comments on your work or during class, or in a number of different ways, not to use the verbiage normal. Right? Up to this point, we shouldn't have been describing distributions as normal because we haven't properly defined it. As I said, a normal distribution or something that is approximately normal has to fit specific criteria, and that's what we're going to start getting into right now, is the criteria for being normal. All right. So, all normal curves have the same overall shape. They are symmetric, single-peaked, right, unimodal, and bell-shaped. Right? The bell-shaped means that they taper down on both sides of the curve. Any specific normal curve is completely described by giving its mean, mu, and its standard deviation, sigma. Right? So a normal curve is using the mean and standard deviation of a population. Right? We're using mu and sigma. So if we look at our little graphics here, we have two different normal curves. They're both bell-shaped, unimodal, and symmetric. The mean, right, and median, right, are right here at the center of the curve. We then have sigma right? 1 standard deviation to the right, notated here, and where that point will be, like from the mean to 1 standard deviation goes to here. All right. And in this one, obviously it is less spread out, so the standard deviation is a little narrower. So, one more slide with a couple other bullet points about normal distributions that we're going to do. You raise your hand if you need a moment to write these things down. Okay. All right. In a normal distribution, the mean is located at the center of the symmetric curve and is the same as the median. Changing mu, the mean, without changing sigma, standard deviation, moves the normal curve along the horizontal axis without changing its spread. Right, this is based on what we learned in last class, that if I add or subtract a constant, it changes the location of like the mean and the median and where the like quartiles or percentiles reside, but it does not change the shape or the spread. Right, so if mu changes, but sigma doesn't, the curve stays the same. Right, we just shift everything up or down the axis. The standard deviation sigma controls the spread of a normal curve. Curves with larger standard deviations are more spread out. And that's in this example here. The area under the curve has to be 100%, has to be 1. So we can't have really a curve that is like as spread out as the one on the left here, but as tall as the one on the right. The area would be too large. So, right, if it is more spread out, it's like shorter. Less spread out, taller. Right? And that's the only options, right? We can't have a super tall, super spread out distribution. It won't work out. And as a preview or a peek into where this goes, in order to have distributions that have a total area of 1, right? One of the things that we can do is standardize the scores. That's why we looked at standardized scores or z-scores. If I standardize my results or my distribution, it converts it all to something that will have an area of 1 under the curve. Okay, so that's why we've looked at that, because when we have an area of 1 under the curve, we can use other tools to learn percentiles and describe our distributions better, but use like tables of values to find more values and find more information. So it allows us to do a little bit more with the statistics. All right. you guys have any questions? And can you raise your hand if you need time to write any of these things down from this slide? Seems like we're good. So, last thing. I need to make sure that I've covered what I needed to so you guys can do to check your understanding. So, let's look at that real quick. I'm going to do that. I need to stop sharing the screen. And that. Go here, go here, there. All right, so back to sharing the screen. Yes, excellent. All right. So we have our week 9 CYU here. I did embed a small calculator into the directions so that if you need a calculator, it's right there. We have the question about percentile, question about z-scores, essentially. We have our cumulative or relative frequency, which is something we covered, I believe it was last week. And our fourth question, yeah. I didn't cover quite enough for us to do this one. This question shall be moved to next week. All right, so I'll edit this real quick, guys, because I did not review how to actually draw a distribution yet based on our standard deviation and the mean. So please don't start this quiz yet. I need to adjust it. No one has started it yet. And remove the fourth question. We'll place that one on next week's stuff. All right, so give me a few minutes after class if you're planning on doing this right after class so I can fix that and make it more appropriate. All right, so there we go.